Okay, so this in fact gives some tangent vector field, and also is the volume form if it's interpreted as a form, and I'll explain what the volume form is right now. Yes, there is this here. Yeah. So we need orientation more precisely to do integration. So let M be a smooth manifold of dimension n. Maybe I should start using D like in the preprint, or use n. I use D in the preprint for dimension, so maybe better to use D. Okay. Then since omega d of m is one-dimensional, although it's possible that it doesn't have global dimension, but at least locally, because globally it might not have globally defined. Maybe I think there are, but at least locally it's one dimension. And if there exists a function, a form, a D form, omega, so this is element of D, which is non-zero at any point, which is the same as i.e. if omega is f the x1 to the xd, this is f the x1 to the xd, this is the form of omega, then f is non-zero. Everywhere non-zero. It's everywhere non-zero on M. F is smooth function. Okay. If there exists, then if there exists such thing, then we say that M is orientable. And choice of such a choice of such omega and identifying all multiples of omega with a positive function, of omega with a positive function, is called an orientation. of M. And if M is orientable, it has two orientations. We write if M is connected. So okay, it should be connected. I don't define what this, but it means that it's not split into two parts or more. If M is connected, so cannot be split into open non-empty sets. U1, U2, such that U1 is M. The union is M, and their intersection is the empty set. Then there are only two orientations, and if M and orientable, so if M is connected on and orientable, it has two orientations, exactly two orientations. So given by some omega, and so the negative of omega defines another orientation. We're working only with orientable manifolds. They're non-orientable. You may have heard of the Möbius strip. If you take a sheet of paper and then twist it on one side, it's not orientable globally. But we're looking with only orientable manifolds, and let's give first example. First, I will do an example for Rn, and then I'll show how to orient boundaries. So Rn, Rd, the integer, has orientations given by dx1 to dxd and minus dx1 wedge dxd. So this is not that interesting, but it's how you orient. Because we have a global functions on Rd, and we can do this form dx1 to dxd, and it's negative. Now let me give some theorem. First definition. No, so in the preprint there is a definition, abstract definition of outward pointing vector field, which works on any manifold. Here I will get some idea, I don't know, of an outward pointing vector field. So if let M this integer, Rm is a D-manifold, and X is a vector field, then X is outward pointing if it points to the outside of M locally applied to the boundary. This is very imprecise definition, but otherwise I will have to do much more definitions, and I don't want to do that. Here's some example. M is, let's first example will be rigorous, the second will be diagrammatic. M is S1, not necessarily, sorry. M is B1 of 0, 0 in R2. So we have, and we define X to be the Euler vector field, X ddx plus Y ddy. Okay, so what does this do? Maybe with boundary. And so if you are here, it goes there. If you're here, it goes there. If it's here, it goes there, and so on. It just doubles the distance and goes in the same direction. It is outward pointing intuitively. Now, example 2 will be something like, if I have, I don't know, something like that. And I'll do some kind of vector field that does this. So this vector field, if I stretch it, it will cross the boundary, but locally it points outside. And this points here, this points here, and so on. This could point here. It's important to point outside. So these are very small. Let's make them big. And this could go there. Okay. Unfortunately, with this definition, we cannot show if we are one-dimensional space embedded in 3, or because it's not boundary of a 3D object. We can make search. So, for example, okay, example 3 would be the sphere. Let it write it up. M is B1 of R3, and again X is X ddx plus Y ddy plus Z d dz. This is again the Euler vector field. So if I'm here, things like that, again I will go to the outside and so on. Okay. So we have the following theorem. I think if it's maybe it's definitional theorem. Let's make it a theorem. So let M be a smooth manifold, this dimension with boundary. Smooth manifold with boundary. Smooth manifold of dimension boundary S. Boundary S. So S is denoted, let me call curve D of M. Curve D, partial D. Then so assume M is orientable with orientation form. I said if we have a form and you multiply by a function, you get another orientation form, but let's fix some omega. Then M has an outward pointing vector field X, and so X is in M, and iota, this is the interior product. I defined it last week, so I will recall what it is. Iota X of omega is, this is in the trace of this thing here. So the trace on D of omega this is in omega D minus 1 of S is a volume form, or I call it orientation form. Okay, it's an orientation form on S, and this orientation is called, because there are two orientations, this is called the induced orientation. This orientation on S is called the induced orientation. Okay. Let's give examples. So first, let M be R2. It's work in any dimension, but let's do it in R2. Not R2, sorry. The half space. So M is 0 infinity times R half plane. So we have the plane like here. Can you suggest an outward pointing vector field. So what is the outward direction? Left. So x, so y could be 0, so there will no dy, and we'll have x will be minus dx, something like that. And omega will be dx which dy. And so on the boundary, so this is the boundary. So the boundary of
It doesn't sound like a vector field, it's more like a
ddx, sorry. Yeah. And S is the line. So S equals when y equals x equals, so sorry, so 0 times r. Yes. This is S. Now, iota is y. And this is, so we had again here the Leibniz rule. Let me write it here to get more space. Minus, I will just put the minus on the outside. So this is minus iota ddx dx wedge dy, and we have minus because it's a one form, and Leibniz rule says that if the first term is a negative degree, we have minus sign, and this is minus dx wedge iota ddx of dy. How much is this? Do you remember?
what?
This is 1. So this is, okay, let me write in full. So this is dx of dy minus wedge dy of ddx. This is 1. I'll have here brackets. This is minus 1 dy minus dx, and this is 0 because and so we get minus dy. So the natural orientation here is down. Let's do for, let me just generalize this. So this is generalization of 1. D is integer and n equals 0 times power of e, this dimension, and then x is minus d dx, and omega is dx1. This is this wedge dx2 to dx d plus 1, let's say. And here I should put trace here. So trace of iota e of x of omega will be, if you apply the Leibniz rule many times, anytime you have terms from this of this which doesn't have dx1 will be 0. So we only have the first term. So this will be minus dx2 wedge 2 dx d plus 1. With another example, ask why not, and then we go to disk 3. No, yeah, disk, and then we get a ball. So m equals what's this? B100, and S is S1. Dm is S1, the unit circle. So we have x, we set is x ddx plus y dy. And omega is again dx wedge dy. And then so let me write this as, let's write this as omega m, and omega s is the trace of iota x of omega m, and this is the trace of iota e, not iota, e x d dx plus y d dy dx wedge dy. I remember when I was doing calculus 3 course, we're doing some kind of clockwise, counterclockwise, doing some kind of heuristics, but here you have a definite way to find orientations on the boundaries. You just need a little bit more of tools, but what you have. So x of d dx wedge dx wedge dy will remove the first part. So this will be trace of x dy, and then this term will remove the second one, but with negative sign. Maybe I could write it in full. Okay, I don't write them in full. X dy, and here y d dy of dx wedge dy. So this will be this at the iota of this with this wedge with this minus this with the iota of these two. So because the iota of these two is 1, we have minus with the x part, and we get minus y dy. And we did this calculation previously in polar coordinates, this vector field, the circular vector field. So this in polar coordinates, so in x equals cosine phi, y equals sine phi, this is d phi. Oh, this is dx. Yeah. Okay. Let's, if I do it for a disk, no, we can calculate for a ball the orientation on a sphere this way, but next time I will, because I don't have time today, I will do it in a different way. So yeah, I mean, if you want, you can try for ball. M equals B1000 is R squared. R2 is a ball, and the M is S1. And then if X is X ddx plus Y ddy plus Z ddz, and omega M is dx wedge dy wedge dz, you can find that omega s, which is trace of iota x omega m, will be in polar, in not polar, in spherical coordinates. Let me just check, because there were, I think it was sine theta d theta d phi, something like that. Let me check. This is in it's 6.9 in the current version of the preprint. So in spherical coordinates, I use these coordinates. Like, okay, I wrote this many times, so I will not repeat. Phi is the rotation and theta is the azimuth angle. This thing here is true for all points except the Greenwich meridian, and you have to do many charts and glue them. So it's not a global formula. This is also not a global formula here, because the circle has not a, doesn't have a single coordinate system. But in most standard coordinates, looks like that. So yeah. This term sine theta, in some sense, represents the fact that it has curvature. The sphere has curvature, and the circle doesn't have curvature, because a circle can be unfolded into a line, but you cannot unfold a sphere into a line, into a plane. So I will get now very, I mean, strong definition of integration by using, why not? Let me just check to do everything right. First, let's define a compact manifold. Let D is integer. M is subset of RD. We say that M is compact if it is closed and bounded. Bounded meaning it doesn't go to infinity. It stays inside, so it stays inside some finite ball. This is bounded. Enclosed if it's um, complement is open. Example, and closed end bricks. So closed end bricks and their boundaries. And two closed balls, let's say D balls, and their boundaries, which are D-1 spheres. So all circle spheres are closed, closed circle, closed disk, closed. Both are compact sets. Okay, and now let's define integration. Let the I don't need forms. Okay, let M be a compact, smooth manifold, orientable, compact, smooth, orientable, oriented manifold. And integration okay, and dv the dimension of M integration on M is a linear map integral of M from D forms to real numbers with the following properties. I'm not sure if it's the most strict definition, but it's, I think it defines uniquely the following properties. So first, if it's so, this is not defined on a single manifold, it's defined on non-manifold. If M is M1 united to M2 with the same orientations, then the integral of M and omega is D form. Then integral is additive, so integral they don't intersect. Sorry, M is so, and omega 1 and of if it's disconnected. Okay, if M is disconnected. This is just some property to work on points. So integral of M of omega is integral of M1 the trace to M1 of omega plus integral of M2 trace. Here I forgot to say M1 intersection M2 is the empty set. So we have some additive property. This is change of variables. If N is another D-manifold, and phi from M to N is diffeomorphism preserving orientations. Then we have, and omega is in omega bullet of N, or omega D of N. Then the integral on N of omega is the same as integral of M of F P star of omega. Three is the Stokes-Cartan, maybe Stokes-Cartan. If omega is a D-1 form, then integral of M of the omega is integral of the boundary of M with the induced orientation, it's assumed. And now people usually don't write the trace, but we need to write induced orientation, it's assumed. And now people usually don't write the trace, but we need to write the trace of omega. People omit the trace and write integral of M d omega is integral of the boundary of M of omega. And 4 we have base case. So integral of a single point. So if M is a zero manifold, and epsilon is an orientation of M, then integral of X, let's say, and F is function. So it's a function of single argument. Then f of x, integral of a single point is epsilon times f of x. So it depends on the orientation. We are over time, but let me give some example. This thing here did generalize all the theorems in calculus for integration and boundary. So first, let's compute integral of in 1D. So D equals 1. Integral of df, let's say from in the set AB. Let's call this I, and this is integral of AB of f prime x dx. Okay, this is on the other side. You know this is f of b minus f of a, but let's see why. E is integral of the boundary of AB of the trace of f, which is the same f, but trace of f. Trace in the boundary, which is so of m. Sorry, of f, which is so the point. If you have this line here, this is oriented negatively, so this has minus orientation, and this has plus orientation. So this is integral of minus. So this is formal to write this in that way. Maybe I can write it this way. So this is integral of b with minus 1 and sorry, a with minus 1 and b with plus 1. And the trace on the set AB f. And this is a sum of two integrals. So this is integral of a with minus 1 of f plus integral of b with plus 1 of f. I omitted the traces, and this is minus f of a plus f of b. So this is Newton-Leibniz. So this is Newton-Leibniz. If you have d equals 2, and then so this is 2, this is 1. 2.1 will be integral of df of some gamma. Gamma is a curve. So gamma is a curve. In 2D. Then the integral of f df is integral of the boundary of gamma. And this is gradient theorem. maybe trace this thing here. Gradient theorem. It depends on the orientation. So if the curve is from here to here, we would take with this plus and this with minus. This is gamma. So this is start. So this is A0, this is A1. Sorry for being here, but I want to finish this. I hope nobody has anything guessed. So let's say M is a region and integral of M and omega is one form. Then integral of gamma of M of the omega is integral of the omega dm of trace of omega. This is Green's theorem. I will give example for Green theorem, which is no, maybe. Do you need example for Green's theorem? No time. Okay, let's finish in 3D. Maybe next time. I want to write all of this. 3.1. Gamma is a curve oriented. Here also oriented. Oriented. Is an oriented curve in 3D. And then gamma and f is function on gamma. Then integral of gamma of df is integral of the gamma of trace of f. This is gradient theorem in 3D. (3.2) S is a surface, 2D surface is a surface, and omega is a two-form. Smooth, okay, smooth. Omega is a two-form. Then integral of m of s d omega is the same as integral of ds of trace of omega. And because this was like curl, this is Stokes Kelvin-Stokes theorem. This is D1. And last one, M, this is R3, sorry. M is a region and omega, here this is a one form, so not two form. Omega is now a two form. Then integral of M d2 of omega is integral of the M of trace on the boundary. And this is Gauss divergence theorem, because this is like divergence. This is Gauss divergence. theorem. Okay. Maybe next time I'll give some example with green, but we have no time. So the point is that Stokes-Cartan theorem that I gave as an axiom generalizes all theorems of integration of vector calculus and one-dimensional calculus as well, the Newton-Leibniz. So there were 6 theorems now into one single theorem.
This will be